Hi, Lakshay. Welcome to the podcast.
Hey Robin, nice to be here. Thanks for having me.
Fantastic. Let's begin with a brief intro to yourself.
Sure. So my name is Lakshay Sharma. I'm a computer vision slash ML scientist and engineer. Presently, I'm with Instacart, based out of New York City, where I work on problems related to estimated time of arrival prediction. So using AI, ML for that sort of stuff. Before that, I spent about 5 years with Microsoft's geospatial division, where I was using computer vision for things like finding roads and buildings in aerial imagery, finding traffic signs, traffic lights, crosswalks, that sort of stuff in street side imagery. Also doing sort of more traffic and mobility oriented tasks like figuring out when traffic builds up in cities, things like that. Yeah.
Fascinating. So we connected on Torch Geo. I'm very interested to learn a bit more about your research. Do you mind giving us some intro to that?
Absolutely. So my areas of interest are broadly, I think things that I am very passionate about. Those include self-supervision and computer vision, and more specifically, self-supervision as it's applied to geospatial pre-training. I've also worked a little bit sort of on at the intersection of vision and language, so pre-training. Very classical contrastive style pre-training for vision language alignment, that sort of
Hmm.
stuff.
And self-supervised learning and pre-training has become very significant recently because of the advent of foundational models. But for those that are not familiar with self-supervised learning, can you give a small overview?
Yes, absolutely. So generally in computer vision and machine learning, there are tasks that we care about. So a very common one is semantic segmentation, right? Where there's a certain predefined set of classes we're trying to classify every pixel into. However, very often these tasks, because they fall in this paradigm of supervised learning, they require labels, which can be a very expensive and time-consuming undertaking. So self-supervised learning is this idea where we train these models on some kind of auxiliary task first. And the idea there is that the labels or the supervision for the auxiliary task is it's free because it's some inherent property of the data distribution itself or of the images that we're dealing with. And so the idea there is that if you train on an auxiliary task which is sufficiently challenging and you do it with enough data for enough number of epochs for enough time, you obtain some useful representation of the image that this model can produce. And then this property, these parameters of the model can then transfer better to the downstream task, as opposed to directly trying to train on the downstream task.
Hmm. And how is this similar or different to the original ImageNet pre-training that people might be familiar with?
So it's similar in that both of these ideas are classified as what we would call transfer learning, where we train a model on something first, and then we train it on the task that we actually care about. The difference here would be that ImageNet pre-training does rely on human annotated labels. So the ImageNet data set has about 1,000 classes exactly, actually. And so this idea of transfer learning sort of began around then when folks realized that, okay, we can pre-train a model on ImageNet and after that do the tasks that we actually care about. And then those properties, those desirable properties in the model transfer better to the downstream task. The difference with self-supervision is that it does borrow this idea of transfer learning, but the labels in the task that we tackle first are they don't require human annotation. So in some ways, you can if you have enough images, you essentially have infinite labels with self supervision.
Hmm. Right. So more recently, as you say, we've moved to a self-supervised approach, unlabeled data that allows you to use basically every image that you have available. What kind of approaches have people taken, and how has that evolved over the last couple of years?
So within vision specifically, broadly, I would say there are three umbrellas of approaches. The very first one that was probably very popular maybe about 8 years before now. I'd call it predictive style self-supervised pre-training. Um, okay, how about this? I'll list all of them out first, and then I'll do a deep dive into each one. So there's predictive self-supervision, there's generative self-supervision, and then finally there's contrastive self-supervision. Predictive style self-supervision is where we try and predict some sort of label that is directly derived from the image. It does not require human annotation. It's some property of the image itself. So that's predictive. The second one is generative. So that's, as the name suggests, you're basically trying to reconstruct the image. So the most natural way of doing this is autoencoder style pre-training, where there's some original image that is fed through a few different neural network layers through a bottleneck, typically, because you don't want to make the task trivially simple such that an identity matrix can just recreate it. And then from that bottleneck, the image is then reconstructed through expanding neural network layers. So that would be an example of generative. Of course, there are other more popular ones now, like GANs, where um, quite a popular one for a while, and now there's more like diffusion style generative pre-training. And finally, there's contrastive pre-training, which is by and large, I'd say, the like sort of dominant paradigm at this time. So this is where um, the network needs to sort of cluster or contrast semantically similar inputs together, and then also push apart dissimilar inputs. So an example of this would be maybe the very first the initial set of contrastive pre-training approaches would do this sort of thing where you have the original image, you apply some sort of transformation, some sort of distortion, some alteration to that original image, pass both of these through maybe a Siamese style neural network, and then try to push these two views of the same image together. And anything else that is not from the same image is pushed apart. And this idea has then broadly been expanded to other things where you can take the same an aerial image of the same area, but from two different points in time, and then you can sort of push them closer together using some sort of contrastive loss, and then push apart images from other areas.
Right, fantastic. So you just touched on some of the sort of remote sensing twists on the approach. That'd be a nice point to dive into maybe some of the other approaches that you've seen, or specifically what your research has tackled.
Yep, absolutely. So as I said earlier, the contrastive style pre-training, that's perhaps the dominant paradigm at this time. And a lot of the state-of-the-art models that we see, use this idea. So the DINO series of models from Meta, which that same idea that's been borrowed by some geospatial machine learning teams. That's a combination of like using a contrastive style learning loss, but also they combine this idea of self-distillation, where there's a teacher model and then there's often a smaller student model, and you're trying to sort of contrast views from the teacher model and the student model together. The thing though with contrastive style pre-training is that while it's a very elegant approach, a very elegant mathematical formulation, it does require a vast amount of data. So you probably need hundreds of thousands, maybe even millions of images to make it work pretty well. So that's with contrastive style pre-training. With more traditional predictive style pre-training, some examples of that were very popular a few years ago, actually, where you could drop the color channels from an image, and then you have a grayscale image, and then you're trying to predict the colors. So you're trying to predict some inherent property of the image. So if you see there's grass and trees, but they're grayscale, you could naturally infer that they're green, and then you hope that the model can predict this from the image. Some other popular approaches were randomly rotating an image. So maybe there's a 90-degree rotation to the image, and the model needs to classify what the angle of rotation is. This could be a classification task. You can just have four predefined rotation angles, or you can make it a regression task where it's trying to predict a specific number. The reason a lot of these approaches have actually been applied to geospatial data, but very often these approaches, they sometimes just don't make sense for geospatial data because of the fact that geospatial images have rotational invariance. So you could rotate a picture of a dog and you can tell that, okay, this dog is upside down. But if you have an aerial image, you could rotate it and it still makes sense. So sometimes these approaches just don't transfer well to the geospatial domain.
Fantastic. You touched on, I guess, some of the challenges in terms of the data volumes, etc. And I guess that would create a barrier to use, right? So
Yeah.
efficiency is a big part of the equation in recent years.
Yeah, absolutely. So what we're seeing with the most successful models is the fact that there's a vast amount of training data and therefore a vast amount of compute that is required in this pre-training exercise to then get sort of a general purpose model that can transfer well to a multitude of geospatial remote sensing tasks. There has been less of a focus on sort of efficient pre-training and more targeted pre-training. And that's where my co-author Alex and I focused our energies on, was trying to figure out, can we pre-train efficiently and do it in a way that works well for the very specific downstream task that we care about.
Right. So the downstream task being classification?
In our case, specifically, it was semantic segmentation, actually. So because pixel level classification, to this day remains such a central, maybe one of the most common things that you typically do in remote sensing. So some examples would be land cover classification, where you're trying to figure out if some land area belongs to some predefined set of classes like water bodies or forest cover or things like that, buildings, roads. Change detection, of course, is also a very popular task where given two views of the same area, you're trying to figure out if some pixel in that image had undergone some change or not. And so therefore we picked semantic segmentation, A, because it's a very common task in remote sensing, and B, because it's also very expensive to do pixel-wise labeling.
Yeah, probably the most common task for at least medium resolution imagery. As you say, annotation at the pixel level is incredibly time consuming and therefore expensive. So you have set up your objectives in terms of the downstream task. You said you want to be more efficient. How did you go about tackling that?
So we tried to design a pre-training task that was sort of more closer in the mechanics of how it operates with our target task, which was semantic segmentation in this case. So I can speak to the specifics of the idea, which was actually fairly simple. So we reasoned that given an image, if there's a sub image within that image, or I try not to use the word patch because it's such an overloaded term now with VITs and such. So I'm going to say sub image, but it's a patch really is what it is. So given some image and a sub image within it that you can sort of copy over. If a network is provided both of these and then asked to localize within the full image where this patch was pulled out of. Important distinction here is that we're not cropping this patch or the sub-image out. We're leaving it untouched in the original image, but then we're just making a copy of it, so to speak. And then if both of these are passed into a network, and then this can be treated as a semantic segmentation task, right? Because the network is then tasked with doing a binary pixel-wise classification where it can say that this specific pixel within the original image belongs to the extracted sub-image, or it's a background pixel that does not belong to the original sub-image. So the idea is pretty simple. It's just localizing within a whole image where the sub-image came from as a pixel-wise classification task.
Yeah, that sounds very intuitive. And in terms of, I guess, how you set that up, what kind of distances are kind of reasonable? Is there a gradient that you have to apply in terms of starting with small distances, moving to larger distances, etc.?
I think so. There were definitely a lot of hyperparameters that we had to play around with to sort of make this work because this could be a trivial task if it's just a pixel-wise
Mm,
matching exercise effectively, right? Some of the things we had to do is we had to apply image augmentations independently to the sub-image and the original image. So you can think of this as once this sub-image has been copied over, has been extracted, you could rotate it. You can add some Gaussian noise. You can jitter the color. You can do, all manner of things to it so that it doesn't remain a trivially simple task for the network.
mm,
That was one. We also found that the size of the subimage matters a lot. If it's too small, it becomes a really difficult task, and the network
mm,
doesn't really truly unlearn like useful semantics from the pre-training. If it's too big of an image, then it becomes too easy. Because this is just a binary pixel-wise classification. If the subimage is say 80% of the area of the original image, you can randomly pick a pixel and classify it to be a positive label, and you have an 80% chance then of being right.
mm,
So there's that like balance. Um, I think you mentioned something about the gradient. I think we didn't end up having to focus a lot on things like vanishing gradients, exploding gradients, but we did find that the loss function can affect the pre-training performance and therefore the downstream performance. So
mm,
because this is a there's a because the pixel is kind of a smaller the sorry, I don't mean the pixel, I mean the subimage is a minority of pixel in the original image. There's this like class imbalance. And
mm,
so there we rely quite heavily on very traditional very well studied loss functions. Like the focal loss is a good one for
mhm,
this situation where you have an imbalanced set of pixels, where pixels that are harder to classify or are in a minority are penalized harder in the loss
mm,
function, and therefore the gradients from those tends to be stronger than easier to classify pixels.
mhm. Makes sense. And in terms of the evaluation, what kind of evaluation did you perform and how did it compare to, I guess, the alternatives?
So since this was a pixel-wise classification task, we went with mean intersection over union, which is generally, I think, a good intuitive way to evaluate pixel-wise classification. The alternative would be you could do something very simple like class-wise accuracy, but that doesn't take into account the fact that you have this sort of uneven distribution of classes, right? So the positive labels are always going to be in a minority because to make this task sufficiently hard. So MIoU is the evaluation metric that we went with for this pixel-wise classification task. And I mean, this was not our brainwave. We see that this is very common in semantic segmentation, and so
Mhm.
yeah, that's
Fantastic. And so you pre-trained and you want to demonstrate, I think, superior performance on downstream tasks. How did it perform then?
so we had a few different training setups that we attempted. So what are the things we can vary here? We can attempt different network architectures. We can try a few different data sets. We can, vary the downstream data set so that it's a different data set, a different distribution from the upstream data set. And so these were some of the things we tried. I can walk over them one by one. So we attempted two architectures. One was a VIT style, a DINO V2 model specifically, so which is a vision transformer, which is sort of the more popular architecture now because it tends to model long range dependencies better than traditional ConvNets. Well, I say traditional, but they're only about 10 or 15 years old at this
Mhm.
point. And then we also tried CNNs, a Resonant 50 style backbone, because those are still very effective. As we know, they're less parameter heavy than very often than transformers, more efficient because, as we know, transformers the the runtime complexity, it scales as a quadratic function of the number of patches that we divide the image into. So we saw value in trying both of these architectures. We pre-trained one of our initial set of experiments. We pre-trained on the let me see, I'm forgetting the data set name very quickly. Let me look it up. We tried a few different data sets, and okay, we started with land cover AI actually. So we pre-trained on the land cover AI data set, which is aerial imagery from I think somewhere in Poland, if I remember correctly, and there are I think five, maybe seven distinct land cover classes. So in the pre-training, of course, we don't need the labels from the data set. We don't need these land cover classes. We just do this localization sub-image overlap pre-training task.
Mm.
And so we pre-trained for about 150 epochs with some of those augmentations and some of those things that I was describing earlier. What we found was that the augmentations do matter. So doing something like jittering the colors of the image, that makes the task quite hard, and therefore it's more difficult for the model to learn from this. And the training, if we see the validation loss, it's quite unstable in the pre-training. We found that just doing simple flipping of the image, flipping and horizontal, vertical flips and mirror images of either the patch or the full image. And remember, these are augmented very independently to make the task challenging. So doing that did help the pre-training quite a bit. And we so once we did this pre-training and we picked our best performing pre-training model, then we fine-tuned on the same data set on land cover AI downstream. And we did find that our model actually not only had better performance than a model that used pre-trained weights from, say, ImageNet or from the LVD dataset, which is what DINO is pre-trained on. So we have better performance by about 1 to 3 percentage points,
Mm.
which maybe isn't a huge difference, but I think the biggest difference we saw is in the convergence speed. So our model tends to converge significantly faster than the DINO V2 pre-trained model on which was pre-trained on LVD or say ImageNet ResNet 50. So
Mm.
this was one set of experiments where we had the same data set downstream. And then the natural question we asked is that, hey, we don't want to, because this whole paper was about being efficient, we don't want to pre-train every time on a new data set, given that we want to do the downstream task on some other data set. So therefore, the next thing we attempted was we used the same weights as the land cover AI dataset pre-trained model, and then we varied the downstream dataset. So we tried two different datasets. We tried the Love DA and Deep Globe datasets, both of which also are semantic segmentation. These are aerial images, and there are semantic segmentation labels for land cover classification available for both of these data sets. And we were able to reproduce the same result where we had a bit of a bump in performance with pre-training versus without. But the big win here was that the convergence was significantly faster across all these experiments. Even when we changed the downstream distribution, we pre-trained on land cover AI, but then the fine-tuning happened on Love DA or on Deep Globe.
All right. So I guess the takeaway there is you pre-train once, you perform that pre-training for all different downstream tasks, and then the downstream fine-tuning is just much faster, and therefore more practical.
Right. The one caveat I'd had here is that when you say downstream task, we tried this only on semantic segmentation, but we did change the data set. It is a natural question, though. What if this was not a semantic segmentation task at all? What if this was, say, classification? What if it was object detection? That is not something we were able to try in this set of experiments, but we did prove that doing the same task, i.e. semantic segmentation, but on a different data set does transfer well.
Hmm. And is this something that you see other teams taking this sort of approach, varying the pre-training task? And if so, what other kind of approaches do you see being experimented with?
I think within within geospatial pre-training specifically, what we're seeing is that there's what I think I personally have seen the trend towards uh, more large-scale pre-training with approaches that generalize well to a number of different tasks. And so, which is, I mean, it's a very worthy endeavor, not taking that away from those pre-training approaches. But of course, that comes at the cost of you need a lot of data to pre-train with. And so we actually did do some experiments where we try to measure the efficiency of our pre-training with some of the other well-known geospatial pre-training tasks, pre-training models. So one of the experiments that we tried was we um, we had our pre-trained model. We had a ResNet 50 pre-trained model that we pre-trained on our task, and then we took some of these other weights that are openly available in TorGeo, actually. So this is a good plug for TorGeo. If you want to do some experimentation and you need weights from seasonal contrastive or Satvis pre-train or a lot of the models you can think of, TorGeo makes it super easy to load those weights. So the experiment that we tried specifically here was we pre-train using our pre-training task. And then we fine tune downstream on, I'm forgetting the specific data set we use, but if I'm remembering correctly, it was Deep Globe. And then we have some performance numbers for our pre-trained weights. Following that, we then use the same architecture, ResNet 50, but we preload weights from a few different well-known pre-trained models. So these included Satvis pre-train, GASL, which stands for Geography Aware Self-Supervised Learning, SECO, which stands for Seasonal Contrastive. We also tried ImageNet pre-trained weights and random initialization as a baseline. Um, so the goal here was to not just benchmark performance and convergence speed on this downstream deep globe task, deep globe segmentation task, but also to then compare what is the size of the pre-training data set that we're using. So what we found was that we did better or as well as all of the other model. There was, I think, SSL for EO S12, which was slightly ahead of ours in terms of the mIoU performance. But we were able to beat all of the other models, all of the other pre-training. And we actually converge faster than all of these other pre-trained weights that we tried. And the big takeaway here is that the reason this result is so significant is because we use orders of magnitude fewer images, fewer spatial pixels in our pre-training. So we only had about 7,000 pre-training images from Land Cover AI, and I think about 300 validation images. Whereas all of the other models, they use anywhere between a million to 3 million images, which is the case of SSL for EO S12. So yeah, we had models that used maybe over 100x the number of images, or over 100x the number of spatial pixels as we did, and we are as good, if not better,
Mm.
than those models. One other important finding that I actually forgot to mention in our initial set of experiments with pre-training on land cover AI and then also fine-tuning on land cover AI is I mentioned that gap in performance and convergence. If the amount of label data is reduced, that gap increases quite drastically. So as an example, I'm going back to my paper. So when 100% of the downstream label data is used, there's maybe about a percentage points worth of difference in performance. But if you use 50% of the label data, that gap increases to somewhere between 3 to 5%. If you use a quarter or 25% of the label data, that gap in performance and convergence actually keeps increasing. So that was another important finding we had.
Mhm. And there's lots of kind of contemporary criticism about foundational models and pre-training just being very kind of resource intensive. This sounds like a very promising alternative direction for those kind of scenarios where you're constrained on compute or available data. Maybe if you're working on some kind of niche platform, say, or you have a limited data set in total. This sounds like a really promising direction.
Yeah, absolutely. I mean, of course, the most common and the most, I think, practical way of doing these things is try to find a model that has been pre-trained on a vast amount of data that is known to generalize well, and then fine-tune it on whatever
Mm,
it is that you care about. But what if you just have a very niche task and you just want to do some very specific pre-training targeted towards your specific task, towards your specific data set? That's, I think, really where our approach brings value. One other thing that we didn't actually try because we were trying to make all this work on one single T4 GPU is you could actually pre-train on a lot of data. We only pre-trained on about 7 to 10,000 images, but what if you could pre-train on 1 million images, right? What if you could do the sub-image overlap task on 1 million images and then compare it
mm.
and then see how the performance downstream varies? That is something that I'd be very curious to see.
Love it. Throw that out there for the next paper. Well, thanks
Absolutely.
for covering that topic. Really interesting, and like I say, slightly taking in a different direction from what a lot of what's happening in the field is taking. What's the name of the paper and where is it published?
So this paper, it's titled Sub-Image Overlap Prediction, Task-Aligned Self-Supervised Pretraining for Semantic Segmentation in Remote Sensing Imagery. Very wordy, but if you just search for sub-image overlap prediction, it should show up. This was published at the Computer Vision for Earth Observation workshop in March of 2026, March of this year, and this was a part of the WACV conference, which I think stands for Winter Conference on the Application of Computer Vision. Happened in Tucson, Arizona this year. It's in Orlando next year. One of my favorite conferences. Highly recommend if you're considering attending a conference.
Hmm. And hit the water parks afterwards, I guess.
Exactly. Yeah, I think that's definitely appealing.
Fantastic. All right. So if people want to follow along your updates, is LinkedIn the best platform?
Yes, yeah. So I can be found on LinkedIn, Lakshay Sharma, my full name. There you may find other people with the same name, but if you suffix that with Instacart or Microsoft, I think that should be my profile that shows up.
Fantastic. I'll drop the details in the show notes. And once again, thank you for joining me and all the best for the future.
Awesome. Thanks so much, Robin. Thank you.
Yeah.